Imagine a world where it rains molten glass, where a year lasts mere days, and where the sun looms so close that the planet is locked in a perpetual, scorching embrace. This isn't a scene from a science fiction nightmare. It's the reality of hot Jupiters, gas giants that orbit their stars so tightly that their atmospheres are quite literally evaporating away. But hot Jupiters are just the beginning. Out in the cold, dark void of space, untethered to any star, rogue planets drift alone, untouched by the warmth of a sun. These are the extreme exoworlds, and their discovery is rewriting everything we thought we knew about planets and their place in the universe. Stick around, because what we're about to explore is not just out of this world. It's beyond anything we've ever imagined. The wild side of the cosmos. In the vast expanse of the cosmos, there exist planets that defy the norms we observe in our own solar system. Hot Jupiters, for instance, are gas giants that orbit perilously close to their parent stars, completing a full revolution in just a few Earth days. Unlike our own Jupiter, which takes nearly 12 years to orbit the Sun, these exoplanets are scorched by intense stellar radiation. Temperatures on their surfaces can soar above 10 degrees C, hot enough to vaporize metals like aluminum and magnesium. The gravitational forces at play are also extreme, with tidal forces stretching and compressing the planet, generating immense internal heat. This is a far cry from the relatively sedate conditions of even the innermost planet in our solar system, Mercury, which experiences temperatures up to 430 degrees Celsius, but lacks the massive size and complex atmosphere of a hot Jupiter. Rogue planets add another layer of cosmic weirdness. These are worlds that do not orbit any star, but instead drift freely through the galaxy. Detached from the warmth and light of a parent star, they are shrouded in perpetual darkness and cold. The conditions on these planets are extreme, with surface temperatures plummeting to near absolute zero. Unlike the planets in our solar system, which are bathed in solar radiation, rogue planets rely on internal heat sources, such as residual heat from their formation or radioactive decay, to stay somewhat warm. The challenges of studying these planets are immense, as they are incredibly difficult to detect due to their lack of a bright star to reflect light off of. However, advancements in technology are slowly unraveling their mysteries, revealing a side of the cosmos that is as harsh as it is fascinating. The uniqueness of these exoworlds lies not just in their extreme conditions, but also in their formation and evolution. Hot Jupiters, for example, are thought to form farther out in their planetary systems and then migrate inward due to gravitational interactions with other planets or the protoplanetary disk. This migration process is violent and chaotic, often resulting in the planet's orbit becoming highly eccentric before settling into a tight, circular path around its star. In contrast, rogue planets are believed to be ejected from their parent systems through gravitational interactions with other massive objects. This violent expulsion leaves them to wander the galaxy alone, a stark contrast to the stable, orderly orbits of the planets in our solar system. Studying these extreme exoworlds provides valuable insights into the diversity and complexity of planetary systems. They challenge our understanding of planetary formation and evolution, pushing the boundaries of what we consider possible. The conditions on these planets are so alien that they force us to rethink our definitions of habitability and the potential for life. While hot Jupiters and rogue planets may not be hospitable to life as we know it, their study offers a glimpse into the wild side of the cosmos, a realm where the laws of physics push matter to its limits. What are hot Jupiters? Hot Jupiters are a class of exoplanets that defy the familiar planetary arrangements seen in our solar system. These gas giants, akin to Jupiter, orbit perilously close to their parent stars, often completing a full revolution in just a few Earth days. Their proximity to their stars subjects them to extreme conditions, with surface temperatures soaring high enough to vaporize metals. Unlike the gas giants in our solar system, which maintain a respectful distance from the Sun, hot Jupiters are cosmic daredevils, braving intense stellar radiation and gravitational forces. Their very existence challenges our understanding of planetary formation and migration, as they are unlikely to have formed in their current locations. The conditions on hot Jupiters are nothing short of extreme. Temperatures can exceed 10 degrees Celsius, hot enough to melt silicate rocks and create a rain of liquid iron and glass. The day sides of these planets are scorching, while the night sides can be significantly cooler, leading to fierce winds that howl at supersonic speeds. Unlike any planet in our solar system, hot Jupiters experience tidal forces that can stretch and squeeze the planet, generating immense internal heat. These planets are also subjected to intense stellar winds, which can strip away their atmospheres over time. Despite these harsh conditions, hot Jupiters have been found to possess atmospheres, albeit ones that are vastly different from those of the gas giants in our solar system. One of the most intriguing aspects of hot Jupiters is their unique orbital dynamics. Many of these planets are tidally locked, meaning one side perpetually faces the star while the other remains in eternal night. This creates a stark contrast between the planet's hemispheres, with one side bathed in perpetual daylight and the other shrouded in darkness. Unlike the planets in our solar system, which have relatively circular orbits, hot Jupiters often have highly elliptical orbits, leading to dramatic changes in temperature and atmospheric conditions. These planets also exhibit orbital decay, gradually spiraling inward towards their stars until they are eventually consumed. This process, known as tidal migration, provides valuable insights into the life cycle of these extreme exoworlds. The study of hot Jupiters has revolutionized our understanding of planetary systems. Their discovery has forced astronomers to reconsider long-held theories about planet formation and migration. Unlike the gas giants in our solar system, which formed beyond the frost line where ices could condense, hot Jupiters are thought to have formed further out and then migrated inward. This migration could be due to interactions with the protoplanetary disk, gravitational interactions with other planets, or a combination of both. The study of these extreme exoworlds has also shed light on the diversity of planetary systems, demonstrating that our solar system is not necessarily the norm, but rather one of many possible configurations. The birth of hot Jupiters. Hot Jupiters are a class of exoplanets that defy the conventional wisdom of our solar system's architecture. Unlike the gas giants in our own backyard, which orbit at a respectful distance from the Sun, hot Jupiters snuggle up dangerously close to their host stars, completing orbits in a matter of days or even hours. These planets are scorching hot, with surface temperatures soaring high enough to vaporize metals. Their very existence challenges our understanding of planetary formation and migration. Unlike Jupiter, which is a frigid world with an average temperature of around -108 degrees Celsius, hot Jupiters can reach temperatures exceeding 10 degrees C. This extreme heat causes their atmospheres to puff up, making them appear larger and more bloated than their cooler counterparts. The birth of these extreme worlds is a tale of chaos and migration. Unlike the sedate, circular orbits of the planets in our solar system, hot Jupiters are thought to form farther out in the protoplanetary disk, where ices and volatiles are abundant. However, their stories take a dramatic turn. Through a process called orbital migration, these planets spiral inward, drawn by gravitational interactions with the disk or other planets. This migration can be smooth and gradual or violent and chaotic, depending on the specific dynamics of the system. In some cases, hot Jupiters may even be flung inward by gravitational interactions with other massive bodies, a process known as dynamical instability. This is a stark contrast to the relatively stable and orderly formation of the solar system's planets, which formed in situ and maintained their positions over billions of years. The conditions on hot Jupiters are nothing short of extreme. With surface temperatures hot enough to melt iron, these planets are far from hospitable. Their atmospheres are likely turbulent and dynamic, with fierce winds and violent storms. The proximity to their host stars means they are subjected to intense stellar radiation and winds, which can strip away their atmospheres over time. Despite these harsh conditions, hot Jupiters are some of the easiest exoplanets to detect and study, making them valuable targets for astronomers. Their unique characteristics provide a window into the diverse range of planetary systems that exist in our galaxy, challenging our preconceived notions of what a planet can be. The study of hot Jupiters has revolutionized our understanding of planetary formation and evolution, highlighting the dynamic and often chaotic nature of the universe. Rogue planets. The cosmic nomads. Rogue planets, also known as interstellar planets, are a fascinating and enigmatic class of celestial bodies that do not orbit any star. Unlike the planets in our solar system, which are gravitationally bound to the Sun, rogue planets drift freely through the vast expanse of the galaxy. These cosmic nomads are thought to be incredibly common, with some estimates suggesting that they might outnumber stars in the Milky Way. Their existence challenges our traditional understanding of planetary formation and raises intriguing questions about the diversity of worlds that can exist in the universe. The conditions on rogue planets are extreme, to say the least. Without a host star, these planets are plunged into perpetual darkness and frigid cold. Temperatures can plummet to hundreds of degrees below freezing, far colder than the icy surfaces of Pluto or Neptune, the coldest planets in our solar system. However, the internal heat generated by their formation and the decay of radioactive elements could create subsurface oceans of liquid water, potentially harboring exotic forms of life. The absence of a star also means that these planets are not subjected to the same tidal forces and solar winds, allowing them to retain their atmospheres more easily than planets in stellar systems. One of the most striking aspects of rogue planets is their sheer diversity. They can range in size from small, rocky bodies to gas giants larger than Jupiter. Some may have been ejected from their parent star systems due to gravitational interactions with other planets or passing stars, while others may have formed independently in the cold, dense cores of interstellar clouds. The study of rogue planets is still in its infancy, and much remains to be discovered about their origins, compositions, and potential for habitability. The challenges in detecting and studying these elusive objects are immense, as they do not reflect the light of a host star and are incredibly faint. Despite these challenges, astronomers have made significant progress in recent years. Advances in technology, such as the development of sensitive infrared detectors and the use of gravitational microlensing techniques, have allowed scientists to detect several candidate rogue planets. These discoveries have provided valuable insights into the prevalence and properties of these cosmic nomads. As our understanding of rogue planets grows, so too does our appreciation for the incredible diversity and complexity of the universe. The study of these enigmatic worlds promises to shed light on the fundamental processes that shape planetary systems and the potential for life beyond our solar system. How rogue planets form. Rogue planets, also known as interstellar planets, are a fascinating and enigmatic class of celestial bodies that do not orbit a star. Unlike the planets in our solar system, which are gravitationally bound to the Sun, rogue planets drift freely through the galaxy. Their formation is a topic of intense study and debate among astronomers. One prevalent theory suggests that these planets form in protoplanetary disks, much like their bound counterparts, but are subsequently ejected from their home systems due to gravitational interactions with other planets or stars. This ejection can occur early in the planet's life, when the system is still dynamic and unstable. Another theory proposes that rogue planets might form independently in the cold, dense regions of molecular clouds, similar to the way stars form. These isolated worlds could coalesce from the collapse of gas and dust, but without a nearby star, they remain in perpetual darkness. The extreme conditions on rogue planets are difficult to fathom. Without a star to provide heat and light, surface temperatures can plummet to hundreds of degrees below freezing. Yet, these planets might retain internal heat from their formation or from radioactive decay, potentially allowing for subsurface oceans of liquid water. In our solar system, the closest analogy might be the icy moons of Jupiter and Saturn, such as Europa or Enceladus, which harbor subsurface oceans due to tidal heating. However, rogue planets lack the tidal forces exerted by a nearby star, making their potential habitability a complex and intriguing question. The absence of a star also means that these planets are shrouded in darkness, with no day-night cycle. This eternal night would make any potential life forms reliant on alternative energy sources, such as geothermal activity. Studying rogue planets presents significant challenges. Their lack of a host star makes them incredibly difficult to detect. Astronomers typically rely on methods like gravitational microlensing, where the planet's gravity bends and magnifies the light of a background star. This effect is rare and fleeting, making the discovery of rogue planets a serendipitous event. Additionally, the vast distances between these wandering worlds and us mean that direct observation is currently beyond our technological capabilities. Despite these hurdles, the study of rogue planets offers valuable insights into planetary formation and the diversity of worlds that exist in our galaxy. Their unique conditions and isolated existence push the boundaries of our understanding of planetary science and the potential for life beyond our solar system. The lone journey of rogue planets. Rogue planets, also known as interstellar planets, are a fascinating and enigmatic class of celestial bodies that do not orbit a star. Unlike the planets in our solar system, which are gravitationally bound to the Sun, rogue planets drift freely through the galaxy. These lone wanderers are thought to be incredibly common, with some estimates suggesting there could be more rogue planets than stars in the Milky Way. Their existence challenges our understanding of planetary formation and raises intriguing questions about the diversity of worlds that can exist in the universe. The conditions on rogue planets are extreme and unlike anything found in our solar system. Without a star to provide heat and light, these planets are shrouded in perpetual darkness and frigid cold. Temperatures can plummet to hundreds of degrees below freezing, far colder than the icy surfaces of Pluto or Neptune. Yet, surprisingly, some rogue planets might retain internal heat from their formation or from radioactive decay, potentially allowing for subsurface oceans of liquid water. This raises the tantalizing possibility of life existing in such harsh environments, though it would be vastly different from any life we know. Detecting rogue planets is a significant challenge due to their faintness and the lack of a host star to illuminate them. Astronomers rely on techniques like gravitational microlensing, where the gravitational field of a rogue planet bends and magnifies the light of a background star, to identify these elusive objects. One notable example is PSOJ 318.522, a rogue planet with a mass about 6 times that of Jupiter, discovered in 2013. Its isolation and unique characteristics provide valuable insights into the nature of these wandering worlds. The study of rogue planets not only expands our knowledge of planetary diversity, but also offers a glimpse into the dynamic and often violent processes that shape planetary systems. Hot Jupiters versus rogue planets. In the vast expanse of the cosmos, hot Jupiters and rogue planets stand as testament to the extreme diversity of exoplanets. Hot Jupiters are gas giants, much like our own Jupiter, but with scorching surface temperatures that can exceed 10 degrees Fahrenheit. These planets orbit perilously close to their host stars, completing a full revolution in just a few Earth days. In stark contrast, rogue planets are worlds adrift in the galaxy, untethered to any star. They wander the void in isolation, their surfaces frozen and desolate. Neither type has a direct counterpart in our solar system, making them fascinating subjects for astronomers. Hot Jupiters present a stark contrast to the gas giants in our solar system. Jupiter, for instance, orbits the Sun at a distance of about 484 million miles, taking nearly 12 Earth years to complete a single orbit. In contrast, a hot Jupiter might orbit its star at a distance of just a few million miles, completing an orbit in a matter of days. This proximity to their host star subjects hot Jupiters to intense tidal forces and extreme radiation, stripping away their atmospheres over time. The result is a planet with a bloated, puffy atmosphere and a surface hot enough to melt iron. Despite these harsh conditions, hot Jupiters are among the easiest exoplanets to detect, their large size and close proximity to their stars making them ideal targets for transit and radial velocity methods. Rogue planets, on the other hand, are a different breed entirely. These worlds are not bound to any star, drifting through the galaxy in solitary isolation. Without a host star to provide heat and light, their surfaces are likely frozen and inhospitable. Rogue planets are thought to form in the same way as other planets, from the collapse of a molecular cloud. However, due to gravitational interactions with other bodies, they are ejected from their host systems and cast adrift. The Milky Way alone may contain billions of these rogue worlds, each a silent testament to the chaotic nature of planetary formation. Detecting rogue planets is a significant challenge, as they do not transit any star and their faint heat signature is difficult to discern against the backdrop of the cosmos. The study of these extreme exoworlds presents unique challenges and opportunities. Hot Jupiters, with their large size and close proximity to their host stars, offer astronomers a wealth of data. By studying their atmospheres, scientists can gain insights into planetary formation and evolution. Rogue planets, while more difficult to detect, provide a window into the chaotic processes that shape planetary systems. Both types of exoplanets push the boundaries of our understanding, forcing us to reconsider our notions of what a planet can be. As our detection methods improve, we may yet uncover even more extreme and exotic worlds, each one a piece of the cosmic puzzle. The extreme environments of hot Jupiters. Hot Jupiters are a class of exoplanets that orbit extremely close to their parent stars, resulting in surface temperatures that can soar to thousands of degrees. Unlike our own Jupiter, which is a gas giant residing in the chilly outer regions of the solar system, these planets hug their stars so tightly that a year can last only a few Earth days. The proximity to their stars subjects them to intense tidal forces and extreme radiation, creating environments that are utterly alien compared to anything found in our solar system. For instance, the atmospheric temperatures on a hot Jupiter can reach up to 20 degrees Celsius, hot enough to vaporize metals like iron and aluminum. This is in stark contrast to Jupiter, where temperatures hover around -145 degrees Celsius in its upper atmosphere. The gravitational pull from the parent star can distort the shape of a hot Jupiter, stretching it into an egg-like form. This tidal heating generates immense internal heat, contributing to the planet's extreme conditions. Unlike the gas giants in our solar system, which have relatively calm upper atmospheres, hot Jupiters experience violent weather patterns. Supersonic winds, raging at speeds of up to 50 miles per hour, whip around the planet, creating turbulent storms that dwarf anything seen on Earth or even on Jupiter. These winds are driven by the extreme temperature differences between the day and night sides of the planet, as the side facing the star is perpetually roasted while the night side remains in eternal darkness. One of the most fascinating aspects of hot Jupiters is their unique atmospheric composition. Unlike the gas giants in our solar system, which are primarily composed of hydrogen and helium, hot Jupiters often have atmospheres rich in heavy elements like carbon, oxygen, and even metals. This is due to the intense heat, which can break down molecules and cause heavier elements to rise to the upper atmosphere. For example, some hot Jupiters have been found to have atmospheres containing titanium oxide, a compound that can absorb heat and contribute to the planet's extreme temperatures. This is a stark contrast to the atmospheres of Jupiter and Saturn, which are relatively simple in composition. The extreme environments of hot Jupiters present significant challenges for scientists studying these exoplanets. The intense heat and radiation make it difficult to observe these planets directly, and much of what we know about them comes from indirect methods like transit spectroscopy. Despite these challenges, the study of hot Jupiters has provided valuable insights into planetary formation and evolution. For instance, the discovery of hot Jupiters has challenged traditional theories of planet migration, suggesting that these planets may have formed farther out in their solar systems and migrated inward over time. This has important implications for our understanding of planetary systems and the potential for habitable worlds. Surviving the heat. Atmospheres of hot Jupiters. Hot Jupiters are a class of exoplanets that orbit extremely close to their parent stars, resulting in surface temperatures that can soar above 10 degrees C. These gas giants, unlike our own Jupiter, are tidally locked, meaning one side perpetually faces the star, while the other remains in eternal night. The atmospheric conditions on these planets are nothing short of extreme. On the day side, temperatures can be high enough to vaporize metals, while the night side can be cool enough for some molecules to condense. This creates a perpetual cycle of extreme weather, with supersonic winds rushing from the night side to the day side, trying to balance the temperature difference. In our solar system, the closest analog to a hot Jupiter is Jupiter itself, but even it pales in comparison. Jupiter's average temperature is a mere -145 degrees Celsius in its atmosphere, while turbulent, doesn't face the same extreme temperature gradients. The atmospheric pressure on hot Jupiters is also vastly different. On Jupiter, the pressure increases with depth, eventually becoming so intense that hydrogen gas is squeezed into a liquid state. On hot Jupiters, the extreme heat can cause the atmosphere to puff up, making the planet larger and the atmospheric pressure more complex. This puffiness can make the atmosphere more susceptible to loss, as the outer layers can be stripped away by the star's radiation and stellar wind. The composition of hot Jupiter atmospheres is another area of intense study. Unlike the gas giants in our solar system, which are primarily composed of hydrogen and helium, hot Jupiters can have a significant amount of heavier elements. This is due to the extreme temperatures causing complex chemical reactions and even the breakdown of molecules. Water vapor, for instance, can be present on the cooler night side but dissociate into hydrogen and oxygen on the scorching day side. Metals like iron and titanium can also be found in the atmosphere, vaporized by the intense heat. This makes the atmospheres of hot Jupiters a complex cocktail of elements and compounds, constantly changing and evolving. Studying these atmospheres is no easy task. The extreme conditions make it challenging to create accurate models, and the unique chemistry means that many of the spectral lines astronomers rely on to understand planetary atmospheres are shifted or altered. However, advancements in technology and observational techniques are providing new insights. For example, the Hubble Space Telescope and the Spitzer Space Telescope have been used to study the atmospheres of hot Jupiters in detail, revealing the presence of water vapor, carbon monoxide, and even clouds of minerals. These observations are crucial for understanding not just hot Jupiters, but also the formation and evolution of planetary systems as a whole. Rogue planets and the cold of space. Rogue planets, untethered to any star, drift through the vast, cold expanse of space. Unlike the planets in our solar system, which orbit the Sun, these wanderers face temperatures that plummet to near absolute zero. The coldest known place in our solar system, the surface of Pluto, reaches about -229 degrees Celsius -380 degrees Fahrenheit. Yet, rogue planets can be even colder, with estimates suggesting temperatures as low as -270 degrees Celsius -454 degrees Fahrenheit. This extreme cold is due to the lack of a nearby star to provide heat and light. The closest comparison in our solar system would be the icy bodies in the Oort cloud, a theoretical shell of icy objects far beyond Pluto's orbit. However, even these distant objects are not as cold as rogue planets, as they still receive some faint heat from the Sun. The conditions on rogue planets are unlike anything found in our solar system. Without a star, there's no solar wind to strip away atmospheres, so these planets might retain more of their original atmospheres. However, the extreme cold would cause any water to freeze solid, and most gases to condense into liquids or solids. This creates a world where the atmosphere might rain diamonds, as happened on some gas giants, but at temperatures far colder than any gas giant in our solar system. The pressure and density of these atmospheres could also be vastly different, leading to unique weather patterns and geological processes. For instance, the cold could cause the surface to become incredibly hard and brittle, leading to unique tectonic activity. Despite these harsh conditions, rogue planets might not be entirely devoid of life. In our solar system, life exists in extreme environments, from the deep ocean vents to the cold, dry valleys of Antarctica. Some scientists speculate that life on rogue planets could exist beneath the surface, where geothermal heat might keep subsurface oceans liquid. However, the lack of a star makes these planets incredibly difficult to study. Astronomers typically detect exoplanets by observing the dimming of a star as a planet passes in front of it, or by measuring the gravitational wobble a planet induces in its star. Rogue planets, by definition, don't have a star, so they're invisible to these methods. Instead, astronomers rely on rare gravitational microlensing events, where the gravity of a rogue planet bends and magnifies the light of a background star. This makes studying rogue planets a significant challenge, but also an exciting frontier in exoplanet research. The study of rogue planets offers a unique perspective on planetary formation and evolution. In our solar system, planets formed from a disk of gas and dust around the young sun rogue planets, on the other hand, might have formed in the same way, but were ejected from their star systems due to gravitational interactions with other planets. Alternatively, they might have formed independently from the collapse of a dense gas cloud. Understanding these processes could provide insights into the formation of our own solar system. Moreover, the study of rogue planets could help us understand the limits of habitability and the conditions under which life can arise. Despite the challenges, the study of these extreme exoworlds is a fascinating and rapidly evolving field. The mystery of rogue planet origins. Rogue planets, also known as interstellar planets, are a fascinating enigma in the cosmos. Unlike the planets in our solar system, which orbit a central star, rogue planets drift through the galaxy untethered, not bound to any star's gravitational pull. These wandering worlds present a stark contrast to our familiar solar system, where even the distant Pluto maintains its orbit around the Sun. The extreme conditions on rogue planets are difficult to fathom. Temperatures can plummet to near absolute zero, far colder than the icy surfaces of Neptune or Uranus. Without a star to provide heat and light, these planets are shrouded in perpetual darkness, making them some of the most inhospitable places imaginable. The origins of rogue planets remain a subject of intense debate among astronomers. One leading theory suggests that these planets form in the same way as their bound counterparts, within the protoplanetary disks of stars. However, gravitational interactions with other planets or passing stars can eject them from their original systems, sending them spiraling into interstellar space. This scenario is not uncommon in young star systems, where planetary migration and dynamical instability are prevalent. Another hypothesis proposes that rogue planets form independently, not within the gravitational influence of a star. These free-floating planets could coalesce from the collapse of gas clouds, similar to the way stars form. This process would produce planets that have never known the warmth of a stellar companion. The uniqueness of rogue planets lies in their isolation and the challenges they present to our understanding of planetary formation and evolution. Unlike the planets in our solar system, which have been shaped by billions of years of interaction with the Sun and each other, rogue planets evolve in solitude. This isolation makes them invaluable natural laboratories for studying planetary processes uninfluenced by stellar radiation or tidal forces. However, detecting these elusive worlds is a formidable task. Rogue planets do not emit light, making them invisible to traditional optical telescopes. Astronomers rely on indirect methods, such as gravitational microlensing, to infer their presence. This technique involves observing the temporary brightening of a background star as the gravitational field of a rogue planet bends and magnifies its light. The study of rogue planets is still in its infancy, but it holds immense potential for expanding our knowledge of the universe. These extreme exoworlds challenge our assumptions about planetary formation and the conditions necessary for life. As our detection methods improve, we may uncover a hidden population of rogue planets, revealing new insights into the diversity and complexity of planetary systems. The mystery of rogue planet origins is a testament to the enduring curiosity of humanity and our quest to understand the cosmos. Detecting hot Jupiters. Hot Jupiters, a class of exoplanets that defy the familiar planetary arrangements seen in our solar system, orbit their host stars at incredibly close distances. These gas giants, often larger than Jupiter, experience scorching temperatures due to their proximity to their stars. Detecting these extreme worlds presents unique challenges and requires innovative techniques. Astronomers primarily rely on two methods, the transit method and the radial velocity method. The transit method involves measuring the tiny dip in a star's brightness as a planet passes in front of it. This technique is particularly effective for detecting hot Jupiters because their large size and close orbits increase the likelihood of observable transits. The radial velocity method, on the other hand, detects the gravitational influence of an exoplanet on its host star, causing the star to wobble slightly. This method is sensitive to the mass of the planet, making it useful for confirming the presence of massive hot Jupiters. The extreme conditions on hot Jupiters make them stand out among exoplanets. Temperatures on these planets can soar to thousands of degrees, hot enough to vaporize metals. Unlike the gas giants in our solar system, which have well-defined layers, hot Jupiters often exhibit extreme atmospheric dynamics. Their atmospheres can be tidally locked, with one side perpetually facing the star and experiencing extreme heat, while the other side remains in eternal darkness. This creates fierce winds and dramatic temperature gradients. The proximity to their host stars also subjects hot Jupiters to intense stellar radiation and solar winds, stripping away their atmospheres over time. These conditions are vastly different from those experienced by Jupiter and Saturn, which are much farther from the Sun and have more stable atmospheres. Detecting hot Jupiters has revolutionized our understanding of planetary systems. Their discovery has challenged traditional theories of planet formation, which suggested that gas giants should form far from their host stars, similar to Jupiter and Saturn. The existence of hot Jupiters implies that these planets can migrate inward over time, possibly due to gravitational interactions with other planets or disks of gas and dust. This migration process is a topic of ongoing research and debate among astronomers. The study of hot Jupiters also provides insights into the diversity of planetary systems. While our solar system has no hot Jupiters, they are relatively common around other stars, highlighting the vast differences between stellar systems. This diversity underscores the importance of studying exoplanets to understand the full range of possible planetary configurations and the conditions that lead to their formation. Finding rogue planets. Rogue planets, also known as interstellar planets, are a fascinating and enigmatic class of celestial bodies that do not orbit a star. Unlike the planets in our solar system, which are gravitationally bound to the Sun, rogue planets drift freely through the galaxy. These wanderers are thought to have been ejected from their parent star systems during the chaotic early stages of planetary formation. The Milky Way alone may contain billions of these rogue planets, vastly outnumbering the stars in our galaxy. Their extreme isolation subjects them to conditions that are hard to fathom. The conditions on rogue planets are unlike anything experienced by the planets in our solar system. Without a star to provide heat and light, these worlds are shrouded in perpetual darkness and frigid cold. Temperatures can plummet to hundreds of degrees below freezing, far colder than the icy surfaces of Pluto or Neptune. Yet, the interiors of some rogue planets might retain heat from their formation, creating subsurface oceans of liquid water or even exotic materials like superionic water. This stark contrast to the familiar environments of our solar system highlights the uniqueness of rogue planets. Their extreme isolation also makes them incredibly challenging to detect, as they do not reflect starlight or exhibit the telltale wobbles of a host star. Detecting rogue planets is a formidable task that pushes the boundaries of current astronomical technology. Most exoplanets are discovered through methods that rely on the presence of a host star, such as the transit method or the radial velocity method. However, rogue planets do not have a star to betray their presence. Astronomers have turned to alternative techniques, such as gravitational microlensing, to uncover these elusive objects. This method involves detecting the temporary brightening of a background star as the gravitational field of a rogue planet bends and magnifies its light. The challenge lies in the rarity of such events and the need for precise, continuous observations. Despite these hurdles, recent advancements have led to the discovery of a handful of candidate rogue planets, offering a glimpse into the vast population that likely exists. The study of rogue planets presents a unique opportunity to understand the diversity of planetary systems and the processes that shape them. These wanderers provide insights into the dynamics of planetary formation and the chaotic interactions that can eject planets from their birthplaces. Moreover, the potential for rogue planets to harbor exotic environments, such as subsurface oceans, raises intriguing questions about the possibility of life in the universe. While the conditions on these planets are extreme, the resilience of life on Earth suggests that similar forms might adapt to the harsh realities of interstellar space. The challenges of detecting and studying rogue planets are substantial, but the rewards promise to reshape our understanding of the cosmos. The role of gravitational microlensing. Gravitational microlensing is a powerful astronomical tool that has significantly contributed to our understanding of extreme exoworlds, particularly hot Jupiters and rogue planets. This phenomenon occurs when a foreground star passes directly in front of a background star from our vantage point on Earth. The gravitational field of the foreground star acts as a lens, magnifying the light from the background star. If the foreground star hosts a planet, the planet's gravitational field can also influence the light, creating a distinctive brightening pattern that reveals its presence. This method is uniquely sensitive to planets that orbit at large distances from their host stars, or even to planets that do not orbit any star at all, like rogue planets. Hot Jupiters, with their scorching temperatures and tight orbits around their parent stars, are some of the most extreme exoplanets known. They are nothing like the gas giants in our solar system, which are cold and distant. These roasters can reach temperatures of thousands of degrees, hot enough to vaporize metals. Their proximity to their stars means they are subjected to intense tidal forces and radiation, stripping away their atmospheres over time. Gravitational microlensing has been instrumental in detecting these extreme worlds, especially those that are too far from their stars for other detection methods, like the transit or radial velocity techniques, to work effectively. The unique brightening patterns caused by these planets provide valuable insights into their masses and orbits, helping astronomers piece together the puzzle of their formation and evolution. Rogue planets, on the other hand, are even more enigmatic. These are planets that do not orbit any star, drifting freely through the galaxy. They are incredibly difficult to detect because they do not reflect starlight or cause the wobble of a host star. Gravitational microlensing is one of the few methods capable of detecting these elusive objects. When a rogue planet passes in front of a background star, its gravitational field can briefly magnify the star's light, revealing the planet's presence. The duration and shape of the brightening event can provide clues about the planet's mass and distance. These rogue planets challenge our understanding of planetary formation and evolution, as they must have been ejected from their original systems or formed independently in the cold, dark reaches of interstellar space. The extreme conditions on these exoworlds make them fascinating subjects of study. Hot Jupiters, with their hellish temperatures and intense radiation, push the boundaries of what we know about planetary atmospheres and weather. Some of these planets are even thought to have iron rain, with temperatures high enough to vaporize rock and metal. Rogue planets, meanwhile, face a different set of challenges. Without a host star, they are subjected to the harsh conditions of interstellar space, including cosmic rays and extreme cold. Yet, some of these planets may harbor subsurface oceans, kept liquid by geothermal activity. The study of these extreme exoworlds not only expands our knowledge of the universe, but also challenges our understanding of the conditions necessary for life. Gravitational microlensing continues to be a vital tool in this quest, revealing the hidden secrets of these distant, extreme worlds. Hot Jupiters and their host stars. Hot Jupiters are a class of exoplanets that defy the boundaries of our solar system's norms. These gas giants, akin to Jupiter, orbit perilously close to their host stars, completing a full revolution in a matter of days or even hours. The proximity to their stars subjects them to extreme conditions, with surface temperatures soaring to thousands of degrees. Unlike our own Jupiter, which is shrouded in swirling clouds of ammonia and methane, hot Jupiters are likely to have atmospheres filled with vaporized silicates and metals, creating a hellish environment that's difficult to fathom. Their very existence challenges our understanding of planetary formation and migration, as they couldn't have formed so close to their stars and must have migrated inward from colder, outer regions. The host stars of hot Jupiters are often sun-like, but their influence on these planets is anything but ordinary. The intense radiation and stellar winds from these stars sculpt the hot Jupiter's atmospheres, stripping away lighter elements and leaving behind a dense, heavy atmosphere. This process, known as photoevaporation, can significantly alter the planet's composition and even lead to its eventual demise. In some cases, the host star's gravity can induce tidal forces that heat the planet's interior, leading to extreme volcanic activity and further atmospheric loss. The interaction between hot Jupiters and their host stars is a dynamic and destructive dance, with the planet's very existence threatened by the star's relentless energy. One of the most intriguing aspects of hot Jupiters is their unique orbital characteristics. Many of these planets are tidally locked, meaning one side perpetually faces the star while the other remains in eternal darkness. This creates a stark contrast between the planet's scorching day side and its frigid night side, with temperatures differing by thousands of degrees. The boundary between these two extremes, known as the terminator, is a region of intense atmospheric activity, with supersonic winds and complex weather patterns. Studying these phenomena provides valuable insights into the atmospheric dynamics of exoplanets and the processes that shape their evolution. The study of hot Jupiters and their host stars has also shed light on the diversity of planetary systems in our galaxy. Unlike our solar system, where planets orbit in a relatively orderly fashion, many hot Jupiter systems exhibit extreme orbital eccentricities and inclinations. This suggests that these systems have undergone significant dynamical evolution, with planets migrating, interacting, and even being ejected from their systems. The discovery of hot Jupiters has forced astronomers to reconsider their theories of planetary formation and migration, leading to a more nuanced understanding of the processes that shape planetary systems. As our observational capabilities continue to improve, we can expect to uncover even more about these extreme exoworlds and their fascinating host stars. Rogue planets and their lack of stars. Rogue planets, also known as interstellar planets, are a fascinating class of celestial bodies that do not orbit any star. Unlike the planets in our solar system, which are gravitationally bound to the Sun, rogue planets drift freely through the galaxy. These nomadic worlds are thought to be incredibly common, with some estimates suggesting there could be more rogue planets than stars in the Milky Way. Their lack of a host star means they are perpetually shrouded in darkness, with surface temperatures that can plummet to hundreds of degrees below freezing. Unlike Earth, where life thrives under the sun's warmth, rogue planets are subjected to extreme cold, making them inhospitable to life as we know it. The conditions on rogue planets are starkly different from those on any planet in our solar system. Even the coldest known planet in our solar system, Neptune, which has an average temperature of around -214 degrees Celsius, is relatively balmy compared to the frigid environments of rogue planets. These planets, devoid of stellar heat, can reach temperatures as low as -270 degrees Celsius, just a few degrees above absolute zero. Such extreme cold would freeze nitrogen, methane, and even carbon monoxide solid, creating landscapes unlike anything seen in our solar system. The absence of a star also means no day-night cycle, no solar wind, and no auroras, making these worlds truly alien. Rogue planets present unique challenges for astronomers. Detecting these elusive objects is difficult because they do not reflect starlight or emit much heat. Astronomers rely on techniques like gravitational microlensing, where the planet's gravity bends and magnifies the light from a background star to identify them. This method is rare and fleeting, making the study of rogue planets a complex endeavor. Despite these challenges, the discovery of rogue planets has opened up new avenues of research, offering insights into planetary formation and the dynamics of galactic evolution. Their very existence challenges our understanding of planetary systems and underscores the diversity of worlds that can exist in the universe. The fate of hot Jupiters. Hot Jupiters, a class of exoplanets that defy the familiar planetary arrangements seen in our solar system, orbit perilously close to their host stars. These gas giants, often larger than Jupiter, experience extreme conditions that make our solar system's planets seem downright hospitable by comparison. Temperatures on the day sides of hot Jupiters can soar above 20 degrees Fahrenheit, hot enough to vaporize metals like iron and aluminum. In contrast, even the scorching surface of Venus, the hottest planet in our solar system, only reaches about 900 degrees Fahrenheit. The night sides, while cooler, are still far from frigid, with temperatures plunging to a mere hundreds of degrees. This extreme temperature gradient creates fierce winds that howl across the planet at thousands of miles per hour, dwarfing the strongest winds on Earth or even the gas giants in our solar system. The proximity of hot Jupiters to their stars subjects them to intense tidal forces, stretching and squeezing the planets in a process called tidal flexing. This constant deformation generates immense heat within the planet, further exacerbating the already extreme temperatures. The gravitational pull is so strong that it can even alter the planet's orbit over time, causing it to spiral inward towards its star. In some cases, the planet may be devoured by its star, a fate that awaits many hot Jupiters. This is a stark contrast to the stable, nearly circular orbits of the planets in our solar system, which have remained relatively unchanged for billions of years. The extreme conditions on hot Jupiters present significant challenges for scientists studying these enigmatic worlds. The intense heat and radiation make it difficult for telescopes to observe these planets directly. Instead, scientists rely on indirect methods, such as detecting the tiny dip in starlight as a planet passes in front of its star, or measuring the subtle wobble of a star caused by the gravitational pull of an orbiting planet. Despite these challenges, the study of hot Jupiters has yielded valuable insights into planetary formation and evolution. These extreme exoworlds, with their scorching temperatures and tumultuous environments, push the boundaries of our understanding of what a planet can be. They serve as a stark reminder that the universe is full of wonders and extremes that challenge our notions of normality. Will rogue planets ever find a home? Rogue planets, also known as interstellar planets, are worlds that drift through the cosmos untethered to any star. Unlike the planets in our solar system, which orbit the sun, these nomadic bodies traverse the vast, cold darkness of interstellar space. Their extreme conditions are unlike anything seen in our solar system. Temperatures can plummet to near absolute zero, and the absence of a nearby star means they are shrouded in perpetual darkness. Unlike the gas giants in our solar system, which bask in the sun's warmth, rogue planets are isolated, making their environments harsh and unforgiving. The uniqueness of rogue planets lies in their formation and journey. Scientists believe they form in the same way as other planets, from the accretion of material in a protoplanetary disk. However, gravitational interactions with other planets or stars can eject them from their home systems, sending them on solitary journeys through the galaxy. Unlike the orderly dance of planets in our solar system, rogue planets are chaotic wanderers. Their paths are unpredictable, and their fates are uncertain. Some may drift forever, while others might find a new home. The challenge of rogue planets finding a home is immense. For a rogue planet to be captured by a star, it must pass close enough to a stellar system for gravity to take hold. This is a rare event, given the vast distances between stars. Unlike the planets in our solar system, which have stable orbits, rogue planets must navigate the gravitational tug-of-war of passing stars. Even if captured, their new orbit might be highly elliptical or unstable. Unlike the gas giants in our solar system, which have had billions of years to settle into stable orbits, a captured rogue planet might face a tumultuous journey to find equilibrium. Despite these challenges, the possibility of rogue planets finding a home is not entirely bleak. Recent studies suggest that rogue planets might be more common than previously thought. Unlike the planets in our solar system, which are few in number, rogue planets could outnumber stars in the Milky Way. This abundance increases the likelihood of gravitational interactions that could lead to capture. Moreover, the discovery of rogue planets with potential atmospheres and even subsurface oceans adds a layer of intrigue. Unlike the barren, frozen worlds we might imagine, some rogue planets could harbor conditions suitable for life, making their potential capture by a star a fascinating prospect. The search for life on extreme exoworlds. In the vast expanse of the cosmos, hot Jupiters and rogue planets stand as testament to the extreme diversity of exoworlds. Hot Jupiters, akin to our own Jupiter but scorching hot, orbit perilously close to their parent stars, completing a full revolution in mere days. These gas giants experience temperatures soaring up to 20 degrees Fahrenheit, hot enough to vaporize metals. In stark contrast, rogue planets, untethered to any star, drift through the cold, dark void of interstellar space, their surfaces potentially colder than Pluto's. Both types of exoworlds present unique challenges and opportunities in the search for life. The conditions on hot Jupiters are nothing short of extreme. Their proximity to their stars subjects them to intense radiation and tidal forces, stripping away their atmospheres over time. Despite these harsh conditions, some scientists speculate that life could potentially exist in the upper atmospheric layers, where temperatures might be more hospitable. However, the lack of a solid surface and the constant bombardment of stellar radiation make this a challenging environment for life as we know it. Comparatively, our solar system's gas giants, while large and gaseous, do not experience such extreme temperatures or radiation levels. Rogue planets, on the other hand, face a different set of challenges. Free-floating in the galaxy, they lack a nearby star to provide heat and light. This makes their surfaces incredibly cold, potentially dipping below -400 degrees Fahrenheit. Yet, the interior of these planets could retain heat from their formation, possibly harboring subsurface oceans. Some theories suggest that life could exist in these hidden, subsurface environments, shielded from the harsh external conditions. In our solar system, the closest analogy might be the icy moons of Jupiter and Saturn, where subsurface oceans are believed to exist, but the scale and isolation of rogue planets present a unique case. The search for life on these extreme exoworlds is fraught with difficulties. Detecting biosignatures on hot Jupiters is challenging due to their proximity to their stars, which can overwhelm the signals from the planet. Rogue planets, being untethered to any star, are even more challenging to detect and study. However, advancements in technology and observational techniques are steadily improving our ability to study these enigmatic worlds. The James Webb Space Telescope, for instance, is expected to provide unprecedented insights into the atmospheres of exoplanets, including hot Jupiters. Meanwhile, ongoing and future surveys aim to detect more rogue planets, bringing us closer to understanding these mysterious, free-floating worlds. The quest for life on these extreme exoworlds is not just about finding alien life, but also about expanding our understanding of the universe and our place within it. Hot Jupiters and the potential for life. Hot Jupiters are a class of exoplanets that defy the familiar planetary arrangements seen in our solar system. These gas giants orbit perilously close to their host stars, completing a full revolution in a matter of days or even hours. To put that into perspective, Mercury, the innermost planet in our solar system, takes about 88 days to orbit the Sun. The proximity of hot Jupiters to their stars subjects them to extreme conditions, with surface temperatures soaring to thousands of degrees. This intense heat causes the atmospheres of these planets to puff up, making them larger and more voluminous than their cooler counterparts. The gravitational pull from the host star also distorts their shapes, often stretching them into ellipsoids. The discovery of hot Jupiters has challenged long-held theories about planetary formation and migration. In our solar system, gas giants like Jupiter and Saturn reside in the outer regions, far from the Sun's intense heat. However, hot Jupiters defy this pattern, suggesting that they formed further out and then migrated inward due to gravitational interactions with other planets or the protoplanetary disk. This dynamic process highlights the complexity and diversity of planetary systems beyond our own. The study of hot Jupiters provides valuable insights into the mechanisms of planetary migration and the conditions necessary for the formation of gas giants. Despite their inhospitable conditions, the potential for life on hot Jupiters has sparked intriguing debates among astronomers. While the surface temperatures are far too extreme for liquid water to exist, some scientists speculate about the possibility of life in the upper atmospheric layers. These regions, though still hot, might harbor conditions that could support certain forms of microbial life. Additionally, the unique chemistry and dynamics of hot Jupiter atmospheres could lead to the formation of complex molecules that are precursors to life. However, these ideas remain highly speculative, and the search for life in such extreme environments is fraught with challenges. The study of hot Jupiters continues to push the boundaries of our understanding of planetary habitability and the potential for life in the universe. Rogue planets, a different kind of habitability. Rogue planets, also known as interstellar planets, are a fascinating class of celestial bodies that do not orbit a star. Instead, they drift freely through the galaxy, untethered to any solar system. These nomadic worlds present a stark contrast to the planets in our solar system, which are all gravitationally bound to the Sun. The most striking difference lies in their extreme conditions and potential for habitability, which challenges our traditional understanding of where life might exist. Unlike Earth, which enjoys a relatively stable climate thanks to its position in the habitable zone, rogue planets face a perpetual deep freeze. Temperatures on these worlds can plummet to hundreds of degrees below zero, making them seem inhospitable at first glance. However, recent studies suggest that subsurface oceans could exist beneath thick layers of ice, warmed by geothermal activity. This scenario is reminiscent of Jupiter's moon Europa, where a subsurface ocean is believed to exist, but on a much larger scale. The absence of a host star means that these planets are not subjected to stellar radiation, which could potentially make their subsurface environments more stable and conducive to life. Another intriguing aspect of rogue planets is their potential diversity. In our solar system, planets are categorized into terrestrial and gas giants, but rogue planets could encompass a wider range of types. Some might be icy bodies, similar to Neptune, while others could be rocky or even have compositions unlike anything we've seen before. Their formation histories are also likely to be diverse, with some ejected from their parent star systems and others forming independently in the cold, dark reaches of interstellar space. This diversity presents a unique challenge for astronomers, who must develop new methods to study these elusive worlds. Despite their harsh conditions, rogue planets offer a tantalizing possibility for habitability. Life as we know it requires liquid water, a stable environment, and a source of energy. While the surface of a rogue planet might be too cold for liquid water, the interior could harbor vast oceans. Geothermal energy from the planet's core could provide the necessary heat and energy for life to thrive. Moreover, the absence of a host star means that these planets are not subjected to stellar flares or radiation bursts, which could be beneficial for long-term habitability. However, the challenges of studying these worlds are immense, and much more research is needed to understand their true potential. Future missions to study extreme exoworlds. The cosmos is teeming with worlds that defy our terrestrial imagination, and future missions aim to unravel the mysteries of these extreme exoworlds. Hot Jupiters, for instance, are gas giants that orbit perilously close to their host stars, experiencing temperatures soaring up to 0 degrees Fahrenheit. These planets are tidally locked, meaning one side perpetually basks in the star's inferno while the other remains in an eternal, frigid night. In our solar system, Jupiter's average temperature is a mere -234 degrees Fahrenheit, making these exoplanets scorching infernos in comparison. The extreme conditions on hot Jupiters create unique atmospheres, with metals like titanium and vanadium present in vapor form, a stark contrast to the gas giants in our solar system. Rogue planets, on the other hand, are not bound to any star, drifting freely through the galaxy. These nomadic worlds face their own set of extreme conditions, with temperatures plummeting to near absolute zero. Unlike the planets in our solar system, which are warmed by the sun, rogue planets rely on internal heat sources, such as radioactive decay, to stay somewhat warm. The challenges in studying these exoworlds are immense. Their extreme distances and harsh conditions make them difficult to observe and analyze. However, future missions are being planned to overcome these obstacles. The James Webb Space Telescope, for example, is equipped with advanced instruments designed to peer into the atmospheres of exoplanets, including hot Jupiters. Its infrared capabilities will allow scientists to study the heat signatures and compositions of these extreme worlds, providing unprecedented insights. Moreover, upcoming missions like the European Space Agency's Aerial Atmospheric Remote Sensing Infrared Exoplanet Large Survey are specifically designed to study the atmospheres of exoplanets. Aerial will focus on hot planets orbiting close to their star, including hot Jupiters, to understand their composition, formation, and evolution. The mission aims to observe around 10 exoplanets, creating the first large-scale survey of its kind. This data will be invaluable in comparing these extreme exoworlds to the planets in our solar system, helping us understand the diversity and complexity of planetary systems. The challenges are not just technological, but also theoretical. Scientists are constantly refining their models and theories to interpret the data from these missions, pushing the boundaries of our knowledge. In addition to these missions, ground-based observatories are also playing a crucial role. The Extremely Large Telescope, ELT, currently under construction in Chile, will be the world's largest optical and infrared telescope. With its 39-meter diameter, the ELT will be able to directly image exoplanets, including rogue planets, and study their atmospheres in detail. The ELT's advanced instruments will allow scientists to analyze the light from these exoplanets, providing clues about their composition, weather, and even potential habitability. The combination of space-based and ground-based missions will give us a comprehensive view of these extreme exoworlds, helping us understand their unique characteristics and the processes that shape them. The journey to unravel the mysteries of these extreme exoplanets is just beginning, and the future looks promising. The James Webb Space Telescope and beyond. The James Webb Space Telescope, JWST, has opened a new window into the universe, allowing astronomers to study extreme exoworlds like hot Jupiters and rogue planets in unprecedented detail. Hot Jupiters are gas giants that orbit extremely close to their host stars, resulting in surface temperatures that can exceed 20 degrees Fahrenheit. These planets are unlike anything in our solar system, where the largest planet, Jupiter, is a frigid world with an average temperature of around -234 degrees Fahrenheit. The intense heat and radiation from their nearby stars strip away the atmospheres of hot Jupiters, creating dynamic and hostile environments. JWST's advanced infrared capabilities enable scientists to analyze the composition of these atmospheres, revealing the presence of exotic compounds and weather patterns that defy our understanding of planetary science. Rogue planets, on the other hand, are worlds that drift through the galaxy without a host star. These nomadic planets are shrouded in darkness, making them incredibly difficult to detect. However, JWST's sensitivity allows it to capture the faint heat signatures of these elusive objects. Rogue planets present a unique challenge because they lack a nearby star to illuminate them, forcing astronomers to rely on their thermal emissions. Some rogue planets may have formed in the cold, dark depths of interstellar space, while others might have been ejected from their original solar systems. Studying these planets can provide insights into the chaotic processes that shape planetary systems, including our own. The extreme conditions on hot Jupiters and rogue planets push the boundaries of our knowledge. Hot Jupiters, for instance, experience tidal forces that can stretch and compress their atmospheres, creating dramatic weather patterns. Some of these planets may even have glass rain or molten lava flowing on their surfaces. In contrast, rogue planets face a different set of challenges. Without a star to provide heat and light, their surfaces can plummet to temperatures near absolute zero. Yet, some rogue planets might retain internal heat from their formation, allowing them to sustain subsurface oceans or even potentially habitable conditions. JWST's observations are just the beginning. Future telescopes and missions will build on these discoveries, providing even more detailed insights into these extreme exoworlds. The study of hot Jupiters and rogue planets not only expands our understanding of planetary diversity, but also challenges our theories of planetary formation and evolution. As we continue to explore these distant worlds, we may uncover new phenomena that redefine our place in the universe. The journey to understand these extreme exoworlds is ongoing, and each new discovery brings us closer to unraveling the mysteries of the cosmos. The thrill of discovering new worlds. In the vast expanse of the cosmos, astronomers have uncovered worlds that defy the familiar, pushing the boundaries of our understanding. Hot Jupiters, for instance, are gas giants that orbit perilously close to their host stars, completing a full revolution in just a few Earth days. These planets experience extreme tidal forces, with permanent day sides scorched by stellar radiation and night sides shrouded in perpetual darkness. Unlike our own Jupiter, which is a frigid, windy world far from the Sun, hot Jupiters are tidally locked, creating a stark contrast between their hemispheres. The discovery of these planets has challenged existing theories of planetary formation and migration, as they are unlikely to have formed so close to their stars. Rogue planets add another layer of intrigue to the exoplanet menagerie. These are worlds that drift through the galaxy untethered to any star, illuminated only by the faint glow of distant suns. Unlike the planets in our solar system, which orbit the Sun in a relatively stable configuration, rogue planets are thought to have been ejected from their original systems due to gravitational interactions with other bodies. The conditions on these planets are extreme, with surface temperatures plummeting to near absolute zero. Yet, some scientists speculate that subsurface oceans could harbor life, shielded from the harshness of interstellar space. The study of rogue planets offers a unique window into the chaotic processes that shape planetary systems. The thrill of discovering these extreme exoworlds lies in their sheer otherness. Each new find forces astronomers to reevaluate their models and assumptions. Hot Jupiters, with their inflated sizes and high temperatures, suggest that planetary evolution is far more dynamic than once thought. Some of these worlds are so close to their stars that their atmospheres are being stripped away by stellar winds, creating vast tails of gas that trail behind them. In contrast, rogue planets present a different set of challenges. Detecting these elusive objects is notoriously difficult, as they do not transit any star and emit little to no light. Astronomers must rely on innovative techniques, such as gravitational microlensing, to uncover these hidden wanderers. The quest to understand these extreme exoworlds is not just about expanding our knowledge of the universe. It's about understanding our own place within it. Hot Jupiters and rogue planets serve as reminders that the cosmos is full of surprises. They push the limits of what we consider possible, inspiring new generations of scientists to explore the unknown. As our detection methods improve and our understanding deepens, we can expect even more extraordinary discoveries. Each new world we find brings us one step closer to unraveling the mysteries of planetary formation and the potential for life beyond Earth. As we wrap up our journey through the extreme exoworlds of hot Jupiters and rogue planets, let's take a moment to soak in the sheer weirdness and wonder of these cosmic oddities. Imagine a world where it rains molten glass, where the sun looms so large it would blot out half the sky, or where you're drifting through the cold, dark void with no star to call your own. These aren't the gentle, familiar planets of our solar system. These are worlds pushed to the extremes, and they're out there, waiting for us to understand them. Hot Jupiters, those scorching gas giants that hug their stars tighter than Mercury hugs the Sun, challenge everything we thought we knew about planetary formation and evolution. They're not just hot, they're inhospitable in ways we're only beginning to fathom. Meanwhile, rogue planets, untethered to any star, wander the galaxy like cosmic nomads. They're a stark reminder that our solar system, with its neat, orderly planets, is just one small corner of a vastly more diverse universe. So what's next? Well, the universe isn't done surprising us yet. In our next episode, we'll be diving into the mysteries of diamond planets and stealth worlds. These are planets that defy convention, that push the boundaries of what we think is possible. Will they be even stranger than hot Jupiters and rogue planets? Only one way to find out. But for now, let's leave you with this. The universe is a place of extremes, of challenges, and of endless discovery. It's a place where planets can be hotter than stars, where worlds can drift alone in the dark, and where the only limit is our imagination. So keep looking up, keep wondering, and remember, the most extreme exoworlds are out there, waiting for you to find them.